All right, welcome back. Here we go again. We've got another mega Calc 2 integral. So this is number 4. This one features clever algebra, substitution, long division, and our good friend, the natural log function. So it's adventure time. So let's check this thing out. We've got the integral of the square root of x plus the cube root of x over the fourth root of x to the fifth minus the sixth root of x to the seventh. Okay, so the very first thing I want to do is rewrite this in terms of fractional exponents. So this is going to be x to the 1/2 plus x to the 1/3 over x to the, looks like 5/4 power minus x to the 7/6 power. And of course, you might be looking at this and saying, what on earth are we going to do with this? The key is to look at the denominators of all of these fractional exponents. I want to consider the least common multiple of all of the denominators. So I want the least common multiple of 2, 3, 4, and 6. And that, of course, is 12. That's the smallest number, the least number that they all go into. This is going to inspire my substitution. So I'm going to say, well, with that said, so let's let x equal u to the 12th. That, in a sense, is going to tame these fractional powers. And so dx is going to be 12u to the 11th du. Okay, so let's plug that in. We're going to do a bunch of algebra, tidy this thing up. Let's see what we get. So this is going to be u to the 12th to the 1/2 plus u, u to the 12th, that should be. Can we come back from this? I think we can. So u to the 12th to the 1/3, there we go. And this is going to be u to the 12th to the 5/4 minus u to the 12th to the 7/6. And then be careful because we said dx is this entire quantity. So that's going to be 12 u to the 11th du. All right. Let's see what we can do here. So this is 12. This will be, looks like u to the 6 plus 12 over 3. That'll be u to the 4th over, I believe this will be u to the 15th, right? So 12 over 4 is 3. 3 times 5 is 15. 12 over 6 is 2. 2 times 7 is 14. And let's see what we can do here. So let's do some factoring. See if we can cancel a bunch of stuff out here. So here, let's see. What do I want to take out here? I've got some options here. Let's see here. Well, down here, let's see. Let's do this one step at a time. So I can take out a u to the 14th. That'll leave me with, looks like u minus 1. So let's do that cancellation first, and then anything that's left over, we'll see if that plays nicely with the numerator. Just to take this in little bite-sized pieces. Okay, so that seems pretty good so far, to be honest. We've got a good start. So that's u to the 6th plus u to the 4th. Okay, so 11 copies of u will cancel. This will be, it looks like u cubed, right? So that looks like u cubed times u minus 1. And so that's probably telling me that it might be good to see if I can factor out a u cubed here, just for the sake of canceling. So where did that come from again? So I just canceled here. And that was left over. So let's see here. If I factor out a u cubed from the numerator, I've got, looks like a u cubed plus u to the 1st. And I didn't want to factor out any more than that because I couldn't factor out anything else from there that would be helpful. So this is a good place to be. So now this looks like a more typical Calc 2 type integral. Now you want to recall something from Calc 2 here. So if the degree of the numerator is greater than or equal to the degree of the denominator, we want to do long division first. And then specifically long division of polynomials. Okay, so the numerator is degree 3. The denominator is degree 1. And so maybe we should put this on hold and deal with this algebra, right? So let's do long division of polynomials. Okay, so I'm going to put some placeholders in here. So I've got u cubed. I'd like a placeholder for the square term. And I like a placeholder for the constant as well. And that's divided by u minus 1. So that is cubed, isn't it? There we go. Okay, so I could just say, okay, well, this goes into, so I always look at the first term here. This goes into this how many times? Well, it goes in u squared times. That u squared can go anywhere on top. And then I just distribute, and then I'll subtract. So in some sense, I'm taking u squared groups of u minus 1 from this. So it's just a more sort of general way to think about division. So I divide. I'm going to multiply now. So this is going to be u cubed minus u squared. And then don't forget to subtract because I'm taking away u squared groups of this from this. So that's what this means. So this minus this is 0. This minus minus is plus. Bring this down. The idea is this has 2 terms. I'd really like this to have 2 terms when I do my division. So I start off in the same way. So I'm going to look at the first term here and the first term here. And I say, okay, well, this goes into this how many times? Well, it goes in u times. Then I just distribute and subtract. So distribute and subtract. I'm taking u groups of this from this. So this minus this is 0. This minus minus is plus. So that's 2u. And then I just drop down the 0 here. And then same sort of deal. I look here at the first term, here at the first term, and I say this goes into this how many times? It goes in 2 times. And then I just multiply. So 2 times u, 2 times minus 1, and then subtract because you're taking 2 groups of this from this. So this minus this is 0, this minus minus is 2. That must be my remainder, but remember how we write remainders? 2 over u minus 1. Do people still write R2? Is that still a thing? I remember in 3rd grade writing that, but I haven't done that in a long, way too long time. That's the way you want to write remainders, like this. This makes sense. Okay, so what does that mean for us? It means that this integral is equal to this new version. And so I can say, so by algebra, right? So by algebra, this is equal to this. Because we said this divided by this was equal to u squared plus u plus 2 plus 2 over u minus 1 du. Okay, no problem here. So classic, right? Power rules and then a natural log. So yeah, not too bad. So u cubed over 3 plus u squared over 2 plus 2u plus 2 times the natural log u minus 1 plus c, and then we have to back sub. So we just need to remember if x is equal to u to the 12th from before, that was our substitution, then what do you say, x to the 1/12, just by taking the 12th root of both sides, is u. Now, if I wanted to be a bit more precise, I could use absolute value, but since it was in the context of the way the problem was given in the beginning, so I think we're going to assume that this is where it makes sense in the domain of the original problem. So what does that mean for me? Let's see here. So this is going in for u. So this is going to be x to the 3/12, right? If I plug x in there. So 3/12 is 1/4. This will be x to the 2/12. So that's x to the 1/6 plus 2x to the 1/12 plus 2 ln x to the 1/12 minus 1 plus c. And then maybe we'll just rewrite that. Okay, so if I distribute and then rewrite my roots, let's see what happens. So 3 goes into 12 4 times, and this will be, looks like the 4th root of x. This will be 6 times the 6th root of x. 2 times 12 looks like 24 times the 12th root of x plus, we've got 2 times 12 again is 24, the natural log of, looks like again the 12th root of x minus 1 plus c. That was cool. I like that one. That's fun.